Good evening, and thank you for coming to the NYUAD Institute book discussion this evening. It gives me great pleasure to introduce both our guest, Peter Atkins, and our interlocutor, Professor Joel Bernstein. To introduce Professor Atkins to you, he received his bachelor's degree and PhD from the University of Leicester in the area of chemistry, and as a recipient of the Royal Society of Chemistry Meldola Medal in 1969, and taught physical chemistry at UCLA, and then joined the University of Oxford at Lincoln College as a fellow, and was there until his retirement in 2006. Professor Atkins has led a very exciting and extraordinary career in both research and education, and his education has certainly not been limited to his students at the undergraduate level at Oxford, but to the public in general by writing numerous books, particularly the one we're going to be discussing this evening, Galileo's Finger, The 10 Great Ideas of Science. Professor Atkins has also had a prolific career in writing textbooks. In fact, I can't think of a student in many cases in chemistry who has probably not come across one of his books, either for general chemistry or perhaps most used his physical chemistry text, which is in its 10th edition and co-authored with Julio de Paulo. He's written other texts as well, and I want to mention to you that this March, Professor Atkins' text book on being will be released, and we look forward to that particular release to read it. The interlocutor is Professor Joel Bernstein. Professor Bernstein joined NYU Abu Dhabi this past September as one of our standing faculty. He is a professor of chemistry. He earned his bachelor's degree from Cornell University and a master's and PhD from Yale University. The institutions at which he has been a visiting scholar are entirely too many to mention. And he has had a long-standing and highly productive career in teaching and research at Ben Gurion University in Israel, where he was before joining our faculty here at NYU Abu Dhabi. Professor Bernstein's specialty is in the area of crystal structure and crystallography. He's published a staggering well over 150 papers, numerous book chapters, reviewed and edited numerous books, and has given countless talks at universities and colleges around the globe. I'd like to take a moment now to give a warm welcome to both Professor Atkins and Professor Bernstein as they engage in our dialogue.
Good evening, everybody. Good evening, Peter. I'd like to start with talking about the subject we used this evening on Peter's book, Galileo's Finger. The subtitle of Galileo's Finger is the 10 Great Ideas of Science. In the prologue, you point out that you have concentrated on ideas rather than applications. And you note that you have had to be selective and have no doubt that others could have come up with other super spiders of science. I love that phrase, super spiders of science. Nevertheless, the subtitle employs the article the, and not just 10 great ideas of science. I wonder if you could enlighten us a bit more on how and why you made that choice of the 10, and tell us a little bit about which ones you did not include and why.
Well, first of all, I didn't decide to call it the. I always do things that I'm told to do, and my publishers told me to put the article, the definite article there, because they wanted to give the impression that I had really gone out there and selected them, rather than just saying, well, these are 10 serious ideas. These put me on the line for choosing the 10. I suppose it all began, I was reflecting this afternoon on how I would respond to a question like this, and thinking about the history of this book. It all began, like so many things, in a bar in San Francisco, while I was waiting for friends, and I just wrote down on a beer mat 10 great ideas, what I thought were 10 great ideas, and then tested them on my friends when they arrived to late as always. And they thought, yeah, that sounds all right. That's quite a good crop of ideas. Then I had to think of a title, and I came across this title. For those in the audience who don't know what this is, if you haven't looked at the book itself, this is in fact Galileo's finger, because his body was carried long after he had died to from where it had lain for a long time to where it currently lies in Santa Croce in Florence. And an enterprising surgeon saw this arm dangling out of a coffin and happened to have his scalpel with him, and so snipped it off and put it in a jar, so much to the pleasure. And I chose it because I thought it was such a powerful image. And it represents really the change of direction of science from ancient Greek science, when people used to sit around thinking about how the world should be and how it should behave and what's going on without actually going out and testing it. But Galileo really went out and tested it and found and made observations to see how it actually worked. And so this finger really represents a change of direction in science, from ancient science to modern science. And then I had to I think it was retrospectively decide what my criteria were for choosing the 10 great ideas. And I decided that each idea had to be simple, because I think a sign that science has reached deep understanding is to discover simplicity. I mean, if you discover something that sounds really complex and has got to be taken apart even more, then you haven't got down to the bedrock of science. So I needed something simple, but it didn't have to be just simple, because just simple could be stupid. And so what it had to be was simple but pregnant. Simple in the sense that everyone can understand it, everyone can see that this is really a fundamental idea, but out of it springs a whole range of understanding. So it's the ideas had to be like an acorn, which if you plant in fertile minds, grows into a forest of understanding. And I think really nutty, powerful ideas would be my criterion for selecting them. And then coming to write it, you realize that one's limited to 10 because that's a nice compact number, basically. But when you write it, you realize that there's all sorts of ideas. But many of the ideas can be subsumed into the 10 that I chose. So although people might, in the audience this evening, might say, well, why did you leave out X? Why did you leave out Y? Usually I can say, well, X and Y are embedded in the ideas that I've identified. But I'm sure everyone in the audience doing the same thing would come up with a different 10. And it'd be very interesting maybe later on to discover whether people did have different ideas or whether they thought that I had missed some and so on. But I suppose, the short answer to your question after this lengthy response, but I was told to give lengthy responses, was that these are the 10 ideas I'd like to take on a desert island. We have in the UK this program on the radio, which has been running for about 200 years, ever since the crystal set was first made, called Desert Island Discs, where people are invited to take their 8 favorite records, as they're still called, as company on a completely deserted island. And I think my 10 ideas are the 10 that I would like to have as company.
Was there one in particular that you had difficulty in eliminating, that you would have liked to have there in place of one of those 10?
No.
It was a final, no problem.
No problem.
Terrific. Okay, virtually every one of us has had to face the empty page or the blank monitor screen for our waiting for our scientific or literary eureka moment. Each has found a way with dealing with that challenge. I'm often reminded when thinking about this issue of the late Harvard economist and John Kennedy's ambassador to India, John Kenneth Galbraith, who many of you may remember, who was a prolific author, and how he dealt with that challenge. As I heard him tell it, he would run off to his Vermont cottage and force himself to report to his desk at 7:30 every morning, not moving from his chair, not answering telephone calls, not meeting with a soul until 1 p.m., when he would get up, have lunch, and amuse himself in the Vermont countryside, and not return to his desk until the next morning at 7:30 sharp.
Why did he waste the afternoon?
He said he had to get away from writing.
Right.
He just had to get away from writing, and he could no longer concentrate beyond 1 o'clock, and he didn't even try. He even admitted that on to occasional days when not a word went onto the paper. He just sat there all day and was frustrated and couldn't write anything. And I'm sure many of us have suffered the same frustration. But his discipline was never broken. And Peter, you are arguably the most prolific author of chemistry books for general readers, for practicing professionals, and for university and high school students, many who are here. From my point of view, this book is Galileo's Finger, that you suggested as the basis for today's dialogue, is really an intellectual and scientific tour de force. As I read it, I couldn't help pondering about the process that led to this book in particular and your writing habits in general. And I'd appreciate if you could tell us a little bit about those.
Yeah, sure. Well, if the truth be told, I wrote it as an anti-Alzheimer exercise. I think it's so important to keep one's mind active. And so I set out, having thought of these 10 great ideas, to try to understand them. And that took a bit of trouble, you know. One sets oneself Himalayas to climb in some cases. So the actual process of writing this book was to read widely on each of the ideas separately for 4 weeks. So each, to cut a long story short, each chapter took 6 weeks to complete. 4 weeks were trying to understand what it was all about. Just reading very widely. And then there comes a point when you've absorbed the information and you've absorbed the way that other people have expressed the ideas. And you suddenly, something happens inside you that you feel that you can make a contribution that has not been made before. Now, I don't mean like suddenly realizing you can solve the Einstein gravitational equations and so on, which, but I think in terms of an insight suddenly comes to you, an insight that is worth sharing. And I think most scientists have insights about their subject. You well know yourself. And I think it's a duty of a scientist to share an insight, to share the insights they've got, because I think that they have this extraordinary way of looking at the world, and people who are not scientists should demand to share in their insights, and I think it's terribly important. But in doing this book, I think I got to the point when I knew that I could write something that had not been written before on that particular subject. And so wrote for 2 weeks. So my challenge was to read for 4, write for 2 on each of the 10 ideas. And I mean, it's not really a successful anti-Alzheimer's book, because as soon as you've got you've got the end of that particular 6 weeks, I just forget what I. So I've moved on to the next one, and so on. And there's, one's brain is only about the size of a litre, and I don't know how many ideas fit into a litre. I bet you probably have to read some of it to me in order to remind me about
what
some
you
of
wrote.
these ideas. So that was the genesis of this book, and it was a terribly rewarding book. There's no point in writing books if they're not rewarding, because you take pleasure from learning, and it's like teaching. I mean, you take pleasure from teaching, and learning is much the same thing. The actual more general question of my writing habits is, it's normally a sort of 6 o'clock start in the morning, and a 6 o'clock end to the day. So it's a 12-hour day, basically. Normally I've got more than one book on the go at the same time. Galileo's Finger was a little bit different. There was a kind of lull in my schedule, and it had the fields to itself. But normally when I'm doing revisions of textbooks and so on, I've got at least 2 on the go, sometimes 5. That's pretty crippling.
Yeah.
But I imagine if the students actually were to look at them, they were to see that they're all the same anyway. So just didn't realize I was copying out of the morning book into the afternoon book and so on. But actually, there was a rigidity which is perhaps more rigid than JK's rigidity, because I used to work in my college in Oxford, and would work on, if there were just, let's pretend there were 2 books being done. When the college bell struck 2, I would stop the morning book and switch to the afternoon book, even in mid-sentence. That was tough. Sometimes I cheated, of course. But, I mean, that's a wonderful way of keeping multiple ideas in juggling balls, because you've thrown up one ball, the sentence is half finished. You're desperate to catch it. And next morning, the thought is already formed, and you just want to get on. So by having both books in this state of being up in the air, at the end, halfway through a sentence, you're desperate to get from one to the other and then back to that other one. And since you've started a sentence, you don't have to collect your thoughts. You're up and running straight away. Now, with 5 books on the go at the same time, that's really tough, and I can't pretend that I do that. So it just collapsed into a kind of rubble of organization now. But I do work for about 12 hours a day.
But did you come back to a half-finished sentence the next day and
Oh, yeah.
say, what was I thinking there?
No,
what was
no. You read
how
the
do I finish it?
sentence, you know what's going to happen. Yeah.
Terrific.
Then you're up and running. So it's great. I recommend everyone to stop
So what is it?
at stop at a point that you're desperate not to stop at. I mean, it's a great way of...
And 4 or 5 o'clock in the afternoon wasn't a problem to keep going. Your
No,
intellectual
right.
powers were all in high gear.
Now I work from home, and it's jolly difficult. When I say jolly difficult, people understand that English.
Yeah,
This is, yeah.
I think so.
It's very difficult to stop at 6 o'clock, but I tell myself I must. And the way that I decided to make myself stop at 6 every evening, is to have a really serious martini.
That was my next question.
Yeah. Then you creep back to your second martini. I now cheat, and I have a fake martini. So I have a glass, a martini glass full of water. I can almost convince myself it's a real martini. But it's
With an olive or without an olive?
that would be going a cheat too far.
Okay.
A plastic olive.
Okay, let's move on. In the first chapter of Galileo's Finger, entitled Evolution, the Emergence of Complexity, you describe one alternative to evolutionism, namely creationism. In your words, and I'll quote you here, creationism, including its transparently camouflaged variant, intellectual design, intelligent design, sorry, is not science. It is an untestable assertion pursuing and impelled by an anti-science, religiously motivated agenda. That's the end of the quote. Nevertheless, in many countries, there are considerable political and religious pressures to include or to maintain the teaching of creationism as an alternative to evolution, often claiming the need for a so-called balanced view under the guise of democracy and freedom of speech. I believe, myself, that as responsible scientists and teachers, we are not only obliged to present the best scientific theories and interpretations and the factual basis for those theories and interpretations, we must be at the forefront of the effort to resist the populist tendency to provide a legitimate podium for the expression and teachings of these unscientific dogmas. And I certainly would appreciate your thoughts on this matter, which you also raised in your book.
Yeah. Well, to teach creationism is just child abuse. I mean, it's undermining the whole process of human rationality, and it's deplorable. What is really deplorable about the intelligent design people is the way that they distort the evidence, and I think that is disgraceful. I don't mind them having a separate view, but to present material that is simply a lie is inappropriate, and I think people should be aware that they lie. Secondly, I think creationism is laziness. It's very easy to look at a phenomenon or fact in the world and see and say, okay, it's a part of design. We don't have to think about it anymore because it's been designed for us and that's the way it is. Science is extraordinarily hard work and intellectually rigorous and demands the union of minds across the world and across time to ferret out explanations which are deeply buried underneath phenomena and the observations of those phenomena. And I think that humanity should be proud that just by accident it stumbled upon a technique for eliciting truth, the scientific method. It's not much to the scientific method. All it is going out, doing experiments, doing carefully controlled observations, in other words, and then talking about it and making sure that your observations somehow fit into a network of ideas that are emerging from other sources. And that's a wonderful, such a simple process that it's amazing that it took until the 16th century really to be stumbled upon. And now, of course, it's currently fully flourishing. We know that the scientific method is an extraordinarily powerful way of answering all the great questions that concern people in what seems to be, I'll cover my back a little bit there, what seems to be a fully reliable manner. So intelligent design is just simple laziness, driven by prejudice, appealing inappropriately to authority. Whereas science is all about attacking authority, if you like, to undermining it. You don't get Nobel Prizes by supporting authority. You get your Nobel Prize for undermining it and setting up a new paradigm for understanding the world. It's so exciting. And it's extraordinary that the collective human mind is capable of what seems to be limitless. I'd like it to be limitless understanding. I don't know that it's limitless, but I would argue that so far it appears to be limitless understanding. So I don't like the creationists. They corrupt youth by, they undermine, I mean, they set a bad example. They show that authority is what you should appeal to if you want answers. And that's terribly, terribly dangerous. They don't encourage investigation, which is what human intellect is all about, and science in particular is all about. And they don't encourage the thought that the world is comprehensible. And we scientists are in the business of discovering comprehension, and I think that's wonderful. I think comprehension enriches life. I think you don't need comprehension all the time. You can look at a rose and take joy from seeing its beauty and leave it at that. But if you have a scientific moment, and scientific ability, you can burrow beneath the surface and look at the reasons why it's red and get deeper delight. It's like, everyone can listen to a piece of music in a totally superficial, unanalytical way and get great pleasure from it. But if you want to, you can throw a switch if you're musically educated and understand it more deeply by understanding its structure and its cultural significance, its where it fits into cultures of various the worlds, where it fits into the history of musical emergence and so on. Likewise, painting. You can take a superficial view, most enjoyable, but you can deepen it. You can deepen your joy in science when you want to. I think everyone. It's going back to that remark I made all that time ago about sharing insight. I think we scientists have an obligation to help people on that path to deepened joy.
Good, thank you. One of the chapters in Galileo's Finger is entitled Entropy. Oh. And when we met the other day, I told you a little bit about our integrated science course for first-year students, some of whom are here in the audience. And we call that the Foundations of Science. And what we're doing is making an attempt to coordinate the teaching of physics, chemistry, and biology to give these students a better idea of the big picture, where these disciplines overlap, for instance, and also where they may differ in terms of definitions, perspectives, in some cases, even in terms of fundamental concepts. For instance, I was struck by the fact in teaching this course with some physics colleagues that physicists virtually never speak about a concept that's dear to the hearts and minds of chemists, and that's something we call enthalpy, delta H. And another conceptual chasm seems to exist in our view of entropy. One way that we chemists look at entropy, and in the way, in fact, you presented it in your book, is as a measure of the degree of disorder. And when I described it that way in class, where my physicist colleagues were present, they cringed, and even, as I recall, One of them raised a fist in protest. Chapter 4 in Galileo's Finger deals exclusively with entropy. And I know that you've given a great deal of thought to this subject and even published an entire book on the second law of thermodynamics. So perhaps you can enlighten my physicist colleagues and the rest of the audience as well, who may be less familiar with the concept, on how we should view this very important property of entropy.
Yeah, well, when I taught thermodynamics in Oxford, of course I had to teach the first law first. And Jesus, if I can say that. And Jesus, that's so boring. It can be made interesting, but let's pretend it's seriously boring. When I got to the second law, I was able to perk up a little bit and say that no other law of science, in my view, has contributed more to the liberation of the human spirit than the second law of thermodynamics. I think it's really sad to think that people might go to their graves, and I'm not sure how I'm looking at, not knowing the second law and saying why I regard it as such a fantastic law. And of course, as I'm sure many people know, that C.P. Snow, the author, used, and my predecessor in Leicester, in fact, used the second law as a test of scientific literacy, saying that if you not knowing the second law of thermodynamics is like never having read a work by Shakespeare. I imagine that's a totally meaningless comparison these days when no one's read a work by Shakespeare. But you know, and I think I'm pretty sure that Snow didn't understand the second law himself as well. But anyway, he was making, I think, a very valid point. I think the second law is wonderful, and it's held up as being this extraordinarily difficult thing that that no one really understands. But I did prepare this afternoon just a few slides to show you about everything you need to know about entropy. I think people can see around. I mean, and that's it basically. Basically, the second law says that things get worse. But scientists can sophisticate these things. In other words, what they say is that this never happens. It's always the opposite. That matter and energy tend to spread in disorder. Now, what we mean by disorder is where I think I would like to take your physicists aside and have a quiet conversation with them. It is not the place for it in this room. But I would be very happy to take up these pictures with their understanding of entropy in terms of microstates and so on. Very subtle, very interesting. But the point about, there's the second law in effectively a nutshell. But the point about the second law is that it may be possible to tap into that decay, that dispersal of energy and matter, if you've got the suitable machinery, and use it to construct something. So, for example, the red-green blob, might be a hydrocarbon fuel, and the process that it shows in dispersing there is the combustion of the fuel and the spreading of the carbon dioxide and water molecules in disorder, and the spreading of the energy that is released in the combustion. The mechanism might be the actual engine. The blue blocks on the right might be a pile of bricks, and the blue blob, which is constructed out of those bricks, might be a mosque, cathedral, whatever. You can, as a consequence of decay, process on the left, you may be able to construct. The blob on the left might be breakfast. And the process of digestion is this thing on the left. And this chain of mechanism might be the metabolic processes inside your body. And these might be amino acids, which are constructed, are joined together, built together like a cathedral, but made into a protein molecule. So as you eat, so you grow. The second law illuminates that. So there's all sorts of things that, for example, there might be the great disperser in the sky, the sun, which is the energy released in the nuclear fusion processes is dispersing, is captured on Earth by photosynthetic process. And so the biosphere emerges. And the biosphere, so we've seen the link really between the dispersal on the sun and the emergence of the biosphere on Earth. Or, we might eat the biosphere, a fairly Japanese breakfast, but that sort of thing. And out of that, the process of metabolism, grow our organs. So we've now seen the link between the biosphere and our own, the emergence of our processes. And so ultimately we're seeing the link between dispersal on the sun and the emergence of processes, the emergence of organs. And you could even take it further. I mean, it's not too stupid to think, and I think students should certainly feel encouraged to think big when encountering science, because it's the ideas of science that illuminate everything, even the grand concepts of existence. So in this case, you can imagine that there's all sorts of random electric and chemical currents going on inside this brain, a resting brain, if you like. But they can be driven through the metabolic processes, having had breakfast, into some semblance of structure. So you're beginning to see how creative thoughts emerge, and indeed scientific understanding emerges. And the second law is so wonderful because simply as that process of decay, dispersal, random process really, out of it, through it, you can see the growth of structure in all its forms, not just physical structure, but mental structure. I think it's a wonderful insight into. And then the second law is very important because it enables you to think about making things quantitative, and really science isn't just all about lying back and thinking of images. It's taking those images and rendering them quantitative using mathematics. And so once you introduce mathematics into an idea, it acquires enough spine to stand up to experimental quantitative investigation. And so it really becomes a part of the rigorous part of human knowledge. And to understand what goes on, to turn those pictures I've just shown into quantitative ideas, you have to take someone like Rudolf Clausius, one of the 19th century founders of thermodynamics, and look inside his brain. It's kind of Monty Python sort of process. And really realize that he can talk in terms of entropy and so on. But it's up to instructors, and instructors in the broadest sense, and instructors in the sense of you and me instructing our students, but also in terms of scientists going out into the world and illuminating the public, to take equations which talk about the change of entropy, change of disorder, and try to interpret these rather, at first sight, sterile mathematical expressions. And the way that I do this I mean, this is a hugely important, it's the only equation I'm going to show. It's a hugely important equation showing the fact that the increase in disorder, the increase in entropy, is given by the energy transferred as heat divided by the temperature at which it's transferred. So what, students say? So what, I hear you say. But you can put that into a pictorial context by imagining that this temperature represents turmoil, because the hotter things are, the more the molecules are jittering around. And that input of energy as disorder is like a sneeze. I'm going to in a moment. I feel it coming up. It's like the change in entropy is like sneezing in a busy street if the temperature is high. So if you transfer energy in a busy street, there's not going to be much more disorder introduced. So you can see that if the temperature is high in the busy street and you sneeze, there's not going to be, this quantity is small, so the increase in entropy is going to be very small. But if you sneeze in a quiet library, then that corresponds to sneezing in a low temperature environment, because the molecules are quiet. And so even the same sneeze can generate a lot of disorder, as everyone knows, if they sneeze in a quiet library. So this sort of imagery, I think, is very important for conveying the sense of what an equation means and rendering it quantitative. And then you can go on to satisfy engineers and so on by doing all sorts of calculations, which I won't talk about. So entropy is enormously important because it's that measure of disorder. Okay, it's really the measure of, it's the logarithm of the most probable weight of the microstates of a system. But, you know, it's a measure of disorder. And you can understand why things happen because of it. Everything that happens in the universe, everything that happens, what's going on inside you, is really driven by disorder. So, in a sense, the concept of entropy emerged from observations on a steam engine. And you are all steam engines, and in a rather abstract sense.
Fine, thank you. I'd like to cover one more topic, one more chapter out of the book, and that's chapter 7, which is entitled Quanta. It's entitled Quanta, but subtitled The Simplification of Understanding. And again, I'm thinking about what my first-year students are going through these days. I don't think that they would just being introduced to the whole idea of the quantum mechanical model of the hydrogen atom I don't think they would agree that their understanding was simplified by this model. The majority of the people in the audience have probably very little notion of what the quantum theory is all about. But I'm sure they would very much appreciate being enlightened in the same way you just did for us with entropy on the subject. In the middle of the chapter on quanta, in fact, you express the hope that you would be able to reveal to young and perceptive minds the simplicity that quantum mechanics has brought to our understanding of the world, end quote. Well, Peter, you can consider this audience just packed full of young and perceptive minds, and so tell us what the quantum is all about.
I was warned this was coming up, so I prepared a slide. And I decided that there were, this is probably my understanding of quantum, but it will come up in a minute. Of course, you must remember that Richard Feynman said that, effectively said that people who are not puzzled by quantum theory haven't understood it. So if you will go away this evening puzzled, that means you do understand it, right? I'm sure you'll find the logicians among you will not like that. I don't know why that's gone on. Anyway, there's my 5 minutes on quantum theory. I think there's about, I can't remember how many, 5 principles that are important. One is quantization of energy. One is the wave-particle duality. I'll come back to all these, not all of them, some of them. Well, another is, come on, yeah, I made them shadowy because I don't want to talk about them. One was superposition, one was complementarity, and the 5th was entanglement. I'm glad, I don't know if you can see them on these other bigger screens, but I decided that the challenge, if I could get across those first 2, then you know enough about quantum theory to go away and do any examination on it that you're likely to encounter, especially the older ones among you, who of course won't encounter any examinations. Quantization of energy. That means that, let me just do this. Suppose you've got a pendulum, and I've got the closest thing to a pendulum here. Then, according to classical mechanics, it can swing with any energy. So if I just pull it back a little bit, it's not got very much energy. If I pull it back a lot, it's got a lot of energy, and so on. And according to classical mechanics, I could pull it back to any angle and let it swing. So and therefore I can give it any energy I want. So by that graph on the left, you can see all possible energies. All that quantum theory does is to say, don't believe it. It can actually only swing with certain energies. So those are the energies that it can swing with that energy, it can swing with that energy, and it can swing with that energy. It can't swing with an intermediate energy. I mean, what science is so wonderful about is taking the obvious and overturning it. Don't believe your senses. In other words, go out and make refined measurements, because you will discover that your preconceptions are normally false. I mean, the classical view, the view arising really from Galileo and then Newton and his immediate successors, is the obvious thing that this can swing with any energy that I choose, simply by pulling it back, say, an extra micron and so on. I give it a little bit more energy. Not so, says the careful measurer. It is found that only certain energies exist. That's true for vibration, this oscillation of the pendulum, for rotation, and various other kinds of motion. So the quantization of energy is that simply that energy cannot be given to an object in a continuous way. It can be given only in discrete packets. And this is a particularly simple example of that. So that's the quantization of energy. The second principle that I refer to is wave-particle duality. Now, classical physics takes the view that particles are, as I've indicated here, little nutty jobs, okay, that move and that we can keep track of them. Quantum mechanics says, not so. You cannot distinguish a particle from a wave. The concept of a particle and the concept of a wave blend together, and you cannot speak just of one or just of the other. Completely alien to our immediate perception of the world. And this is the beginning of reasons why you should be puzzled. So quantum mechanics is really a way of discovering what allowed energy levels there are in a system. A system might be an atom, a molecule, whatever. And trying to understand how to combine the concept, the classical concept of a particle and the classical concept of a wave into a kind of blended concept. It's very, very difficult to imagine. The basic idea is that a wave simply tells you where you are likely to find a particle. So wherever the amplitude of this wave is high, then you are likely to find a particle. Where the amplitude is zero, such as these points, there is no chance of finding the particle. So you can begin to see that understanding waves enables you to talk about the location of particles in quantum theory. And it all boils down to Schrödinger. There's another Monty Python-esque sort of slide. And Schrödinger came up with a way of calculating the shape of these waves. For most undergraduates, most students, it consists of putting a blank piece of paper in one side of his head and pulling out the so-called wave functions on the other side. But just as we did with Clausius, you have to look inside someone's head to understand what's going on. And inside Schrödinger's head is his equation. And his equation enables you to calculate the shapes of these waves and to relate them to the allowed energies. So in classical mechanics and quantum mechanics, you can see that immediately you start to think in terms of waves. You can see that only certain waves will fit into a container. And so if there is an energy associated with each of those waves, then only certain energies can exist. So you now see how wave-particle duality, the fact that if you're talking about particles, you must at the same time talk about waves, enables you to understand why only certain energies are allowed in the system. And the Schrödinger equation and Schrödinger's work, which he developed in, as he said, I can't remember quite the conversation, but he was on holiday with his mistress at the time. And it was in a fit of erotic passion that he came across his equation and realized that it was right. And lost interest in his mistress, I imagine. But so the excitement of discovery is really what it's all about, and to discover have a very boring mistress and really look for something interesting, like an equation. That might be the way of doing it. But the Schrödinger equation really is as fundamental to quantum theory as Newton's equations are to classical mechanics.
Mr. Chair, where are we on time? One more question. Okay, fine. Okay, in the epilogue to Galileo's finger, you subtitle the epilogue, "The Future of Understanding." And you may have heard here during your visit that one of the declared missions of NYU Abu Dhabi is to provide a training ground and an educational experience for future leaders. As practical scientists, we, and I mean here all of the practicing and budding scientists in the room, do have a responsibility to increase the scientific literacy of the societies in which we live and work. Our leaders and our bureaucrats have to make decisions based on scientific and technical data with serious technological ramifications and consequences. They need not be scientists to make those decisions, but they need to have sufficient exposure to scientists and the way scientists think and work to be able to seek and take advice from scientific advisors and colleagues. This is part of our mission here. And I'd like to, as we close, I'd like to, at least this part of our dialogue, I'd like to get your views on how best we can accomplish that goal of increasing scientific literacy in our population.
do what you're doing here. I mean, it's so important to have events like this where not only students come, but the interested public come. And then, of course, you need to expand what you count as interested public and make sure that they know that if they don't come to events, not necessarily this one, but comparable ones, that if they don't come to listen to insight again, I go back to insight, if they don't come to listen to insights, then they're sadly missing out. And I think they have to understand the nature of the scientific enterprise, which is evidence-based. And so although one might have prejudices, and sometimes those prejudices turn out to be correct, you need to support them by rational thought, by observation, by argument, by evidence. And so I think instilling a sense of thoughtfulness and realizing that even complicated problems can be attacked rationally and give way to sustained attack, sustained intellectual attack. I think that's terribly important. And you know, the world is a technological place. Doesn't mean to say that it's not a beautiful place. It means that through technology and science, the scope for pleasure has been enlarged. Because as I was talking about the rose earlier on, fine, enjoy looking at a rose, no problem. Take pleasure from that. And I certainly don't think science and technology or anything else should get in the way of that kind of pleasure. But when you want to extend your range of pleasure, then you turn to science and the insights that it provides. When you are an economist, you need to know the limits of science. That is, the reliability of science. You need to know how people have arrived at a consensus, whether that consensus is plausible, whether it's international, whether it's local, whether it's held by just one person out on a limb who has got a good media behind him. You need to be able to assess, in short.
I myself am an amateur astronomer, and so I'm not a great fan of the Catholic Church and the obvious persecutors of Galileo, and I find it unbearably hypocritical of them to do things like, I don't know if it was the present Pope or the previous Pope who made an apology for what they did to Galileo and possibly being wrong about certain theories that they had about the cosmos. They're now also doing things like they're very proud of having established an observatory, and several priests are trained astronomers now. I'd like to know what your opinion is of this, of the what the Catholic Church has done.
Change.
Well, yeah. It's pretty deplorable, isn't it? Let me broaden the answer to that. I think there are three classes of people who think, three thinking classes of people. There are scientists, there are philosophers, and there are theologians. And I think that there's a certain distinction between them. One is that a scientist, in my view, is invariably an optimist, in the sense that a scientist doesn't go about his or her duty with its investigations without the expectation of arriving at an answer. Then there are philosophers, and I think it's the duty of a philosopher to be pessimistic, but which means that you shouldn't really listen to what they say, because it's always a rather gloomy prediction about the future. Because they say, we'll never understand the nature of X, where X might be consciousness and whatever, or science is limited and so on. So maybe philosophers should be pessimists, because they are, if you like, some sort of guardian of knowledge. They're the guardians of knowledge. They make sure that the scientists don't run too fast for their own health. But on the whole, philosophers are anchors rather than sails. The scientists are sails, always forging ahead, looking for new lands, tugging against these anchors, which are philosophers. Now, theologians, in my view, are the next rank down. I won't say that. The next rank down in respectability. That they are professional obfuscators. So a theologian really sets out to obscure the truth by denying that, however we struggle intellectually, we will ever come to an understanding. And if we do come to an understanding, it will be in incomplete comprehension. So theologians are, in my view, obfuscators, and should stay beneath the stones where they thrive. So I hope that sort of captures the spirit.
In the very first chapter of your book, you talked about Darwinian theory, and there was one part where you said that there was a theory that every species would soon become extinct. The dinosaurs were the first, and they hung around for quite long, and then after that they were extinct by an asteroid. Do you believe that humans will, in the near future, perhaps possess, finally, the technology to prevent their own extinction?
Yeah, I think there's real danger of, just the natural flux of modifications to DNA might, in due course, result in some sort of corruption of ourselves and our progeny. But I imagine that it's our own stupidity which will get there first. And we might well annihilate ourselves. And it's, I think it's a duty for all of us to struggle to prevent that and make sure that we go on. I mean, although it is almost certain that there is life everywhere in the universe, not everywhere, throughout the universe, the chances that we will ever have communication with it are extremely slender. And so life is a series of little pockets, not able to communicate with one another, but all able to lie back and understand. And I think it's rather wonderful to think that there are pockets of matter scattered through the universe that can understand matter. And it's a shame should any of those flicker and die.
Let me play the role of a philosopher. All the fundamental scientific discoveries were made more than 50 years ago. It's been said that there are more scientists alive today than all the scientists ever lived. Yet, recent decades, we have no more fundamental scientific discoveries. What's your view on this? And if you believe there's going to be a breakthrough, where it is going to be?
Yeah. Well, we have to hang in. I mean, we in the problems that are now. So let me start that sentence again. I mean, there's two sorts of science. One sort of science is going out, applying what we currently know, and gathering information and building on it and so on. Think of medicine, think of biology, think of chemistry and so on. All of them are burgeoning. All of them are expanding, and there is no sign that they're grinding to a halt. But the kind of problems that you're alluding to are the deeply fundamental problems, the problems that lie underneath our understanding, like the origin of the universe, and like the nature of consciousness, and so on. Consciousness, I think those are the two great remaining problems of fundamental science, where it all came from and how we can understand it. And there's going to be two different sorts of answer to that. The understanding of consciousness will come, in my view, from modeling it, from building ever better computers, not necessarily digital computers, but computing machines of some kind that emulate human consciousness and perhaps transcend it. And they might, in due course, help us to understand very deep problems about the nature of physical reality. And then there's a second sort of problem, the origin of the universe, which will be a mathematically expressed theory, which currently scientists are working on, but not rushing towards. Currently there's quite a number of ideas, like string theory and so on, floating around, which are promising, and but they are such difficult problems. And I mean, think how far we've come in 300 years since the mathematization of nature through Newton and Hamilton and pieces like that. In only 300 years, we've got to the point that we can think about the universe 10 to the minus 34 seconds after it was created. I think it's quite an extraordinary surge of endeavor. And the fact that it's going slow now means that we're dealing with really difficult problems. But as optimists, we know we're going to crack it. When? Who knows?
This question may seem a little less sophisticated, but out of your 10 ideas, do you have one that's your favorite, or one that you find most interesting? And why is it the one that's your favorite or most interesting? Yeah,
the second law, for the reasons I gave before, that it accounts for everything. I mean, it accounts for all the processes that occur in the universe, and it accounts for inanimate change. It accounts for the emergence of life. Natural selection and evolution, if you like, is just a way that nature has found to allow the second law to work itself out. With cheetah slaughtering antelope is just really dispersal in disorder in a very deep sense. Of course, that question does raise a kind of meta question there. Whether, and my answer to it sort of reminds me that there is a kind of meta question. I just said that evolution, natural selections are working us out of the second law. So in a funny way, you don't need two separate laws. You could just say the second law, and one of its ramifications is evolution, natural selection. And so the question arises is whether all 10 laws really can be packaged as one, and whether there's only one law that is pushing, governing the universe.